Chapter 4 is all about the carbon molecule. We have talked a little bit about carbon already in the course of talking about life, and now the carbon molecule gets its own chapter. I think you'll like this chapter. It's fairly short. There's just a few things to pull out of it, again, because it sets you up to understand material that's coming after this. We talked about water last chapter, and most life forms are mostly water, so that's H2O. Us as humans, we're somewhere between 70 and 80% water. Actually, women have a little bit more water in them than men, and babies a whole lot more per size than adults. But mostly the rest is carbon-based compounds, so carbon that is covalently bonded to other elements. One of the reasons why this is carbon-based, and you'll probably hear me say this over and over again, that carbon's the backbone of life. So carbon is the thing that other things are bonded to, is it has this ability to form large, very complex molecules that have great variety. So large, complex molecules, but no two are the same. I mean, there are two that are the same, don't get me wrong. I'm trying to generalize this, so I want to make sure I'm saying things general, but not incorrect. But there's a great variety of the way things can get together in terms of their bonds with carbon, because there's 4 bonding sites on carbon, 4 of them, and each of those bonding sites can create a variety of types of molecules. Proteins are carbon-based, DNA is carbon-based, carbohydrates, and many of the other molecules that we recognize as living are carbon-based, living matter. The study of those compounds that are carbon-based, we call it organic chemistry. Most carbon-based compounds are found in living material. There are a few exceptions to that, but most carbon-based compounds either came from something living, meaning fossil fuels, or they are living material. The big exception to that, of course, is carbon dioxide. That's not necessarily, I mean, it's not considered an organic compound, it's considered an inorganic compound. And carbon tends to like to bond to hydrogen. Many times in compounds, you'll see carbon bonded to hydrogen, at least one of those 4, if not 3 of them. The configuration, because there's 4, and this is going to be a 3-dimensional bonding, 4 can form some sort of tetrahedral structure. So we call it a tetravalence, just to get fancy there, I guess. But that tetrahedral shape can be in long chains, or it can be individual. But the other thing about carbon that's unique is it can form double bonds, so it can bond to itself. And when that happens, then you have more of a flat shape. What we're looking here, and you see this often throughout the semester, is we're looking at the different ways chemicals can be expressed. They can be expressed in name, they can be expressed in their molecular formula, their structural formula, their model, we call it the ball and stick model, and then their space filling model. Each one of those communicates something about its properties to a chemist or somebody who studies organic compounds, and communicates something about how this particular molecule might react. So that's why that particular aspect is interesting to look at, maybe not memorize too much or study or be able to be tested on it. Certainly the fact that you have 4 bonding sites, that those bonding sites can be single or double, and those bonding sites tend to form a tetrahedral. Other types of valence or bonding capacity, so the electron configuration of other elements that make up life. They're most frequent partners with carbon, so frequent covalent bonding. And as a matter of fact, because they're so frequent, these are the elements that tend to make up life. You have hydrogen, oxygen, nitrogen, carbon, and then sulfur and phosphate are the only other things that we do find in living matter. Just those few elements, but we have all this variety of life. Hydrogen has one bonding site, so one valence, oxygen 2, nitrogen 3, and carbon 4. And then at the bottom of this particular slide, you see two unique molecular structure, and then also a linear, then a design with regard to the two compounds we're talking about. You have carbon dioxide, which is going to be a linear fashion, and then you have urea, which is carbon with 2 nitrogens and an oxygen, and then 4 hydrogens. And it makes a very unique structure. It almost looks like some sort of spider or something. So a wide variety between linear and this structure that's very three-dimensional. To further explain that point in terms of carbon and its 4 bonding sites and its ability to form a variety of spatial and stick figure and even molecular structures, you have a whole page full of different carbon compounds, the names, and then the linear structure there, the written out formula. Ethane is 2 carbons, propane 3 carbons, and so you have kind of a linear design there. And then you have, if you go all the way down to methylpropane, which is the bottom one, which is branching. So you have you can put carbons together and form a long compound. That would be length. You can double bond them and form a little bit of a flat and then a length, or you can branch them, which between the butane and the methylpropane, you can form a branch off carbon, as well as you can form rings. So you have cyclohexane and benzene, and both of them form rings. The interesting thing about the benzene ring is that you have single bonds and then double bonds. So the variety with regard to carbon's bonding capacity leads to much of the diversity that we have in life. We have some carbon hydrogen bonded material in our bodies, which we use as a storage for our stored form of energy, and those are our fat molecules. So hydrocarbons are considered a very reactive compound. Actually, the gas that fuels your car, as long as you're not totally electric, the gas that fuels your car is actually a hydrocarbon. It's a hydrocarbon because it has the ability to generate a tremendous amount of energy. And all hydrocarbons, all gas came from fossil fuels. It's certainly something that probably that you've heard, because fossil fuels all come from something that was alive at one time. At one time this was alive. It isn't anymore, but it still has that hydrogen carbon bond. In your body, you have on the left side at the top, you have a stained slide of fat droplets. And if you when you ingest calories and you ingest more calories that your body needs at that time, what it's going to do is say, oh good, she ingested some calories. We don't need them right now, but we're going to put them in the bank. So you can kind of think of your fat as your fat bank. And so what happens is fat hydrocarbons, I already said, are very reactive. But what happens is 3 of them together that are bonded together, which we call a triglyceride, they become very stable. You have a nice area that is attracted to water and an area that's repelled from water, but it makes a nice stable molecule, which we call a triglyceride, and then it can be formed. However, it can be used for energy. That's kind of like you put your money in the bank, but you put it in a bank that doesn't let you really take it out unless it's absolutely necessary. And that's what your stored form of fat is energy for you, but your body's not going to let it go unless you absolutely need it. A couple of other terms to learn. You have isomers, and you can have structural isomers. They are have the same covalent arrangement but of their atoms, but different designs. So you can see pentane on the left, same number of carbons, hydrogens, linear, and then you have your 2-methylbutane, and it's branched. And then you have cis and trans, or geometric isomers, where the reactive portion is on, with cis, the reactive portion is on the same side, and with trans, the reactive portion, what I mean by the reactive portion is the bond that is the least stable, are on opposite sides. So you have the same molecular formula, but certainly different arrangements, so it would make these two act in a different way. And then you have those isomers that are mirror images of each other, enantiomers, and they're mirror images of each other. And the thing about these is pharmaceutical companies tend to use these quite often, because many times they will react alike but different. It's very interesting. Your book talks about ibuprofen, and the fact that where the reactive portion is, if it's on one area or the other area, it tends to be 100 times more potent. So these are often studied in the pharmaceutical industry. The thing about carbon-based molecules is you can have 2 that look incredibly alike, but you have maybe one or two areas that are different. And on the left here you have estradiol, and on the right you have testosterone. You've probably heard of estrogen and testosterone. The basic structure looks very much the same. You have 1, 2, 3 rings of carbon, and then one of them actually has several double bonds, and one of them doesn't. And then you have a couple of areas that are the more active areas that are different. So the between the hydroxy, the HO on estradiol, and the oxygen on testosterone, and then the extra CH3 on testosterone. What this does is makes the difference between estrogen and testosterone, and there's a huge difference between the two. However, they are very much related to each other. So our what we considered our hormones of our male and female hormones, very much related to each other, but also very different, just because of these two functional groups that are different, and then also a little bit of a different arrangement with regard to the carbon bonding. We're going to end this one now, and we'll pick it up in just a few minutes on the next one.